So so we have a 3 minutes times 60. That's a second, right? So 180 seconds. Now for each second, you have 44,100 samples. Now each sample, you need 32 bits. Okay, so that means, yes. So 32 times 44,100, that's the space we need for each second. Okay, now we have total of 180 seconds. So that's, okay, I'm glad you actually find this one out. Okay, so that's a total. Typically, so we have, let's say, we have, I think you're right. So you have a 3 minutes times 60. You got 180 seconds. Now for each second, you have 44,100 samples. And each sample, you need 32 bits for music CD. And typically, we don't use bits. When you use a computer storage, we normally use byte. Okay, we use bytes. So 32 bits is the same as how many bytes?
4.
4 bytes, right? So it's 4 bytes. So the number is, what's the number? So that means you should divide these. You should divide the number you got by 8. Okay. So what's the total number? That's 180 times. Oh. Let's see. I'm gonna use the calculator. Oh, I'm glad that you got the number. It's 3.02 megabyte. Yeah. How can we get this? Let's check. Okay, so let's do this. I'm going to use my calculator. So it's so 180 times 44100 times 4. Okay. So we got. So let's say let's forget about this number. So let's say 31752,000 bytes. Okay. Now, normally we don't want to use the bytes, right? We want to actually convert it into a kilobyte or megabytes. So when you convert it into a kilobyte, you divide it by 1024. Okay. So when I divide by 1024, okay, so we actually got the 31007.8 kilobyte. And to convert it into a megabyte, then we divide by 1024 again. So it looks like I got 30 to 8 megabytes. So not the same as yours. Let me try again. Let me just double check, you know. Can you double check them? Can you double check that number? It's a 3 times 60 times 44100 times 4. That's 31 million. Okay. Okay, so it's a 30.28 megabytes. So it's much bigger. It's actually 10 times bigger than the number you actually gave. Okay. Yeah, I guess probably you just missed 1 0. Okay. Now, if we want to store this in the MP3 format, so if you want to play in the MP3 player, so how much space? Now, MP3 player is actually everything else is the same, right? Except, the bit depth is 16. It's a half of the 32. So let's actually take a look at it again. So I think for MP3 player, still 3 minutes. So 180 seconds, and the sample is 44,100, and now it's 2 bytes. So it's half of this. Okay. So basically, using MP3 player, you basically got half of the space. Okay. So this is going to actually save you some space. Okay. So the trade-off is you use 16 bits for the actually bit depth. So you loosen up the quality. Okay. But not much. Personally, I don't see much difference between MP3 player and also the music CD. It's pretty much similar. But maybe for some of the music with a very wide range of amplitude, then so probably you're going to lose some of the actually quality. But for most of the music, it should be okay. Okay. Okay, now let's actually switch to another topic. Now, how can we represent images? Okay. So we know that for the sound, we can actually use the sampling technique to actually convert the analog sound wave into a digital sound wave, right? And then you can actually the very nice thing about digital sound is when you transfer the sound, you don't lose the quality. Now, you only lose the quality when you actually convert from analog sound to digital sound. During the analog to digital conversion, you may lose some quality. You may lose some of the sound quality. But if your sampling is big enough, then that loss of quality is not really that significant. You don't see much. However, the good thing about the digital sound is when you transfer the sound, you transfer the digital music. So you're going to transfer the music as a file, and you're never going to lose anything when you transfer the file. So when you transfer as an attachment to someone else, when you download the music, and you're never going to lose the quality anymore. Okay, when you replay the digital sound, you're going to be okay. So when you actually send another music to another guy, you're never going to lose the quality anymore. The only time you lose the quality is when you do the transfer. That's not the case for analog, because remember, when you use the analog music, the analog, when you transfer the analog actually the sound waveform in the electrical wire, then you're going to introduce some noise. So when the noise is coming, so then your sound music, the quality is going to be actually getting worse, getting worse. Now, the longer the distance, the sound quality is going to be worse. Okay, and normally it's so difficult to restore these sound actual quality loss. So that's the problem with analog sound. So the analog sound sounds like it's okay. You can play with analog sound, but when you actually transfer, an analog sound on a very long distance, then when actually noise is introduced during the transfer, or when you transfer the sound, analog wave through some kind of like a magnetic field, you're going to lose the quality of the sound. Okay, so that's the problem with digital sound. You're not going to lose the sound quality during the transfer. Okay, when you actually, you know, when you send the sound to another people, when you actually download the sound from, say, from California, one of the server in California, when you actually pay some of the money and you get access, you can download the music. When you download this music, it doesn't matter what's the distance between the server and your site. You're not going to lose the sound quality during the transfer. So that's the big benefit of the digital music. Now let's take a look at the image. You know, so image is also an analog data. Okay. So when you have, now think about the image as like your photo, your picture. Okay, you're printed on the actually on the paper. So if you still remember the old days, when you actually print your photos on Kodak, Kodak film. Okay. Now, so when you actually take a picture, the picture going to be actually, printed out on the film. When you actually use the film, and you can print the photo out. Okay. Basically, you're going to use use a chemical actually things to actually, display the photo on a paper, right? Dedicate the paper. So these photos going to be also shown as the analog data. Okay, it's an analog data. Okay, because when you enlarge the data, so you're not going to clearly see how the data is going to be actually, the colors and how these actually the photos can be actually, it's just actually some kind of, because of chemical reaction. So you basically print, put like an ink in some of the area more than the other area. You put some the red in this area, reddish color in this area, based on the combination of the base color. Now, the analog image can also be digitalized, also by sampling. Okay, you can also sample. You can use the sampling technique to digitalize the image. Okay, now during the sampling process, often called scanning, an image will be represented with a two-dimensional grid of small elements. Okay. So for example, if you have a picture here, okay, here's a picture of a house, a car, right? A person. So, and then a cloud, bird, flower, grass or whatever. So this is actually, an image which is actually analog data. So analog basically means it's continuous, data. But when you do the sampling, you're gonna do the scan row by row, and you can scan just one row and pick a small dot. Okay. So you basically divide the image into a very small grid. Okay. Now each grid is like a small square. Okay. Now you can make each of the small square a very small, and so then this called actually the pixel. Okay. Now pixel is the smallest element which contains the same color code. Okay. So now you can make a pixel, each pixel a big one, or make the pixel a small one. So for a fixed size of the photo, you can make more pixel in each column and pixel in each row, right? Okay. So for example, you can actually, cut into like a 100, and here you can cut into 800 or 80. So basically, you need to actually get the 80 points, and you can get a 100. So you basically create a grid of a grade of 80 times 100. So each represent a small dot called a pixel. Okay. Now the pixel is which contains only one color code. Okay. So the value of each pixel is encoded as a number of bits. Okay. Now the value of pixel, you can actually use some number of bits to represent a pixel. Now, how can we do this? Okay. Now you can divide the pixel can. Now take it a simple way. If the photo is white and black, it's a white and black photo, and then each pixel can either be a black or white. So you can use two colors, two numbers, as 0 or 1. Now how big a pixel going to be? How much bit do we need to represent a pixel? For black and white for black and white photo, you just need 1 bit, right? For each pixel. So then you can see that okay, if you have a face, for example, here's a hair, and then you have a black color. This is a white color, white color, white color, black color, black color, black color, white, white. And if you have a gray hair, okay. If you have a gray hair, then you can actually put one black here, and the next one's a white, black, white. So you can actually mix the black and the white to make it looks like a grayish color, right? So you can always use the black or white color to eventually create a black and white photo picture. Now the color of the picture is kind of different, because you may have various different colors, red, blue, green, purple, black. white, gray, and dark gray, dark blue, blue, gray, so light blue, or you may have various different kind of color. But you need to remember that's a science. So no matter how many different colors you may have, these different colors can always be created by mixing some of the basic colors. Okay, that's amazing, right? What are these basic colors? In a computer we have three different basic color. One is red,
Yellow. Okay.
Blue.
Blue.
RGB.
yeah, red, green, blue. I don't know how this actually happens, but this is amazing. It's like a magic. So any other color can be actually created by mixing these three colors. I still don't. I'm still. It's just amazing. I'm still confused how this actually can happen. You know. Okay. So then you can mix these different color in terms of the you can put a different weight on each of the color and create a various different color. So the red color could be, you know, you can use typically people use 8 bits for red color. 8 bits for green and 8 bits for blue. Now, these 8 bits represent a number from 0 to 255. Okay, from 0 to 100. Now, 0 basically means a very light red. So basically, it's this is a very dark red. So it's a, basically it's just the number basically represent the darkness of the color. So this is the lightest, and 0 is lightest. Okay. So basically, for each color, you can actually basically represent it with a number. For example, you can choose the red color number 100, the green 100, blue you can choose 100, and 100. Okay. Then this can actually mix these three actually color. You can make a new color. So let's see. Let me see. Let me show you some of the information. Okay. Let me actually. This is actually. I just find out this RGB color code chart. Okay. So if you pick actually the red number is 100. C is 100. Okay. So you make a gray color. It's kind of gray, right? This is amazing. Now what about the 255? Oh, no, so 255, 255. You're making white color. How does this happen? So this is amazing. This is how you can actually create some kind of digital image. So for each pixel, you can actually use the. So typically we use 24 bits. Okay, so each 24 bits. So we can use 24 bits for each pixel. 8 for the red, 8 for the green, 8 for the blue. And now you can use a different value for the red color, different value for the green color, so you can make, you know, you can make pretty much all the colors you can find, over here. So these are the different colors, So if you want to make like a purple, let's see, I click the purple. Let's see, how's it? Okay. I click some kind of a purplish color. So for this purplish color, the red is actually 204, green 0, there's no green. Blue is actually, so you mix the red and the blue, to create the purple. What about this light green? So yeah, so in this case, looks like a light green, right? So now you can find out green is 255, that's the biggest number. And you have a small, you have a red color code is 153. Blue is 153. So then you're going to make a light green. That's amazing. That looks like black. Red is 0, green 0, blue is 0, that's black. Okay. So that's the RGB color. So now you can remember that for each pixel, each small, picture element, you can actually use 24-bit to generate a color code. Okay, so then these pixel has actually, each pixel has only one color code, and then all these different color put together, you create a picture, a very nice looking picture. Okay, now here's an example. Now this is actually this is downtown Boston. I just pick a small, sample over here, and I just enlarge it. Now you can find out, like, this is a small pixel. Now when the picture is small, you don't see actually a pixel, but when they actually make this particular, area much bigger, then you actually can see the square, right? Each square represent a pixel. So now you have a little purple here. But when you actually look at this side from distance, you're probably actually gonna see you don't see the pixel anymore. But if you actually close to the picture, you can see the actual square, a small square, which represents a pixel. Again, just like the sound, the digital sound case. Now, if you think your picture image is not good enough, what are you going to do? Increase the samples, right? Increase the samples. Okay. So the quality of the digital image is called a bitmap mapped image. The quality of bitmap images depend on two facts. Okay. One is called the density of the pixel. So that means in a small area, if you have more pixels, that means your quality is going to be bigger. And that density of the pixel sometimes called the resolution. Okay. And the other one is the number of bits per pixel. Okay. Now remember, we say that most of the traditional digital image using 24 bits for each pixel. Okay. So that means you use 8 bits for the red, 8 bits for the green, 8 bits for the blue, right? 8 bits for the blue. Now, that's basically sometimes we call it true color. Okay, we call it true color. But in some of the high quality image, sometimes people use more than 24, and sometimes people use 48 bits, double this 24 for the color code. Now that means you're going to have more color code. For each color, red, you're going to use 16 bits. Green, 16 bits. Blue, 16 bits. Now what's the effect for this? Now instead of $256 different color code for the green, 256 color code for the red. Now you have 2 to the 16 bits for the red. So your color going to be very, very rich. So you pretty much can actually create a very, very nice picture with very, colorful, a very colorful picture. Okay. So that's also going to increase the quality. Okay. So the density, which means the resolution, and also the number of bits for each pixel. The density of the pixel is normally used something called DPI. Okay. So that means dot per inch. How many dots per inch? Okay. So for each inch. So if you want to create like a PDF file, sometimes they are going to ask you, what's the dot per inch? Sometimes it's 300. So that means you have a 300 pixels per inch, per square inch. Now, in other case, when you actually buy a digital TV, right? Remember that the resolution can be recognized, can be characterized using so the number of pixels per screen. So typically like a 1920 times 1080. Sometimes we call this full resolution, full resolution. It's sometimes we call it 1080p, right? That's a full resolution TV, and that basically means they're actually, 2 million, about 2 million pixels. You multiply these numbers, that's the number of pixels. Okay. So you have a 1920 1080. A 4K TV basically increase the pixel. So you basically double the number. So 1920 becomes 3840, and 1080 becomes 2160. Okay, that's 4K. Any questions on this? So the number of bits per pixel, as I say, true color, for true color, we use 24 bits. Okay. So the qualifies how many unique colors are available in the image color palette in terms of number of zeros and ones or bits. let's say if you use 24 bits, it's called the 24 bits encoding scheme, which can represent this. Okay, but there are some kind of 48 bits per pixel, and that's going to provide you a photo with a very vivid picture, so in that case. Okay, let's, I think I'm going to wrap up for today. Right now, it's almost like 10 o'clock. So let's actually quickly look at the second problem. So image, a photograph taken using digital camera with 6 million pixels with 24-bit true color requires 6 million pixel times 24 bits pixel, right? So that's 144 million bits. Okay, how much storage do we need to store the image? $144 million bits. We can divide by 8. So then the million bytes, right? A million bytes about 18 million bytes. Million bytes, it's almost like 18 megabytes. It's not exactly the same because million is actually use the we use the metric, which basically means 18 million means 1800000. But bytes basically million bytes basically means that every time we're going to divide it by 1024. That's the difference. The metric basically use 1000. So that means kilometer means 1000 meter, but the kilobyte basically 1000 means 1024 byte. So there's always additional 24 over there, but it's close. It's a 1024 and the 1000 is very close. So 8 million bytes is almost like 18 million bytes is almost like 18 megabytes. Okay. So, any questions on this? Okay, so if you don't have any questions, I think that's pretty much all I want to cover for today. Next time we're gonna actually talk about another topic called encoding error detecting code. So we're gonna talk about the digital transmission. So one good thing about digital data is you can actually easily send the data on the long distance, okay, through the long distance. Okay, but if you transmit a long distance, then some of the information going to be lost. Because when you transfer 0, then on the other side it may receive 1. So that's possible because of the noise. Okay, so that's something we're going to talk about next Wednesday. Okay, I think that's pretty much all for today. Do you have any questions before I call it a day?
Hi, Professor. I have a question, but not on today's topic.
Okay. So we should talk about this after class. Okay.
Yes.
Okay. If you have no question, then I think that's it. So have a good night.
Thank you, Professor.
Good evening. Good evening.
Hi, Professor. It's regarding assignment 3, question number 2.